There we go. We're recording now, so welcome to the official start of data structures for today. I have a couple of quick announcements and then we'll get into the class material. So the first announcement is that last week I hired a grader for the class. So this shouldn't have a significant impact for you all because all of the assignments have this sort of automatic grading thing. And you'll know what your grade is as soon as you finish it and get that green button or the red button. But essentially what the grader is doing is just copying the information from those test cases into Sakai to help automate that process for me. So if you do ever have an issue with your grades, either a question about what they are, or you think there's an error somewhere, just let me know, send me an email, and I'll take care of that. And you, won't get penalized or anything like that. Just let me know and I'll take care of it. Let's see. Okay, I'm going to share my screen now for us to talk about the other announcements. The first one I want to do is I created a quick issue over here with a link to a discussion about a new Python feature, new syntactic sugar. We're not going to talk in this class about this Python feature in detail at all, but if you are in the place where you're thinking you want to have a software engineering career, or maybe you're going to be going on interviews shortly for summer internships, this would be a good kind of thing to just read up about. That at these interviews, you often have like a portion of the interview that's technical questions, but there's also a portion of the interview where you're just like talking to people, getting to know people, and this is a good kind of thing to chat about just asking people like, oh, what's your opinion on the new syntactic sugar in Python? And you can get people going on rants, going in one way or the other about, oh, I really like it or really dislike it, and you should sort of be able to participate in those sorts of rants and not necessarily like get into fights with people, but developers respect other developers who have strong opinions about things, even if those opinions are like not the same as my own opinions. So I still respect people who have different opinions than me. Just the fact that they have a strong opinion about something means that they kind of care about the tools, have thought about it, are aware of these conversations that are happening. And so people who are more aware of those things, more likely to be good programmers. And so when I'm doing the more technical aspects of the interviews, I'm going to give people more the benefit of the doubt when they've just demonstrated an interest in these other things going on in the community. So I'd recommend just browsing that to see what people are talking about. Let's see, so there is going to be a lab this week. It's not quite posted yet. It'll depend on exactly what we cover today in class. So yeah, not posted yet. I'll have it posted by the end of the day. And today in class, we're going to do two things. First, we're going to talk a little bit more about this PyTest library. So we were briefly introduced it on Monday, talking about these test cases for your homework assignments, working with stacks. Today, the first part of the class, we're going to go over like how I actually sit down and approach programming problems, whether it's for this class or in general, and how to use this PyTest library really efficiently with your debugging. All the sort of notes that you'll need to take for this part of the class are already listed right here. So my recommendation on how to participate in this part of the class is to just kind of try to absorb like the procedures that I'm going through. It'll only be like a 5-minute portion of class, not a whole lot of technical content other than just getting the sense of how I approach these problems so that you can approach them in a similar way. And then after we do that, we're going to start talking about the big O omega theta notation, and there's this notes, the big O PDF file that I asked you to print for class today, and that's what we're going to be going through for most of class. And we probably won't finish it today. It'll probably go on to next week a little bit, and that's okay. Any questions about any of that before we get started? Okay. Then if we scroll up to the top here, you'll see that in addition to this HTML validator link right here, which is the link to your homework assignment, there's a link right here to example homework. And this is what we're going to do at the start of the lecture today. So I'll just click here and we'll see that these test cases are failing right here. And now I'm going to switch over to the terminal and we'll look at these files in the terminal. We'll see what the test cases are. I'll go through how, like the full development process that I go through of fixing these with, and how I go about debugging. So in this repository, it's structured the same exact way as the homework repository is. We have this prens.py file. Go ahead and open that up. And this has a single function inside of it. I've already added a little bit of code, but the code is not correct at this point. And this is code that we saw last time in class. I gave you the full correct version of it. My recommendation is not to have that in front of you while we're sort of doing this part of class, so that you kind of are approaching this from a as fresh of a frame of mindset as possible. And so in one Vim window, I'm going to have this file open, and then in another one, I'm going to open up the test cases. So it's tab E to open up another tab in Vim, and then test/test_main.py contains all of the test cases. And the first thing you'll notice about this balance prins file is, again, that there's not a whole lot of doc tests in here. That in the notes in class, when I pulled those up, I had a bunch of doc tests, but now I only have a single doc test, just enough to give a sense about like what is the input, should this be, and what is the output. And so typically when I'm working on a problem, or when I'm creating a function for myself, I'll just have one, maybe 2 or 3 doc tests, but definitely not more than 3. And if you're looking at other people's code, say a library, they'll kind of follow the same pattern of just have 1 or 2 sort of examples. And the purpose of these doc tests is really just to show you examples of how to use the code, not to be the test cases that the program is using to verify that it's correct. Those test cases are in this test_main.py file. And again, one function in here corresponds to one test case. And most of these test cases, like these top 8 test cases right here, are very simple test cases. They're things that we could have written with the doc tests. But there's this last test case down here, significantly more complicated test case. And this is something that you could not do with doc tests. We'll see in detail what this is doing in a second. So don't worry about the details of that for now. On the right-hand side, I'm going to actually run the PyTest code. So Python 3 --m PyTest, like so. And at the bottom, the very last line is sort of the key summary of how many tests failed, how many passed. So in this case, 4 tests failed. And as a reminder for your homework assignment, your grade on the homework assignment is always going to be full credit minus however many tests are failing. So in this case, if this was your homework assignment, the homework out of 10 points, you would get 10 minus 4 is 6 points on the problem. Okay, so there's 4 tests here, and I need to figure out exactly which of these 4 tests I want to work on in order to make progress on this problem and get the tests to pass. In general, my recommendation is that you'll probably want to start from like the top down. There's no sort of like formal requirement that in the test cases that I'm writing that the simplest ones will be at the top and the most complicated ones at the bottom. But that's just kind of a general pattern for how most of these test cases files are created. Start with the simple and create complicated ones at the end. So that's what we're going to do. I'm going to start with this top one up here. And when we're looking at this test case, we can see that the problem with this test case is that I'm saying, well, let's first take a look at the test case over here. I know which test case I'm running because up here in green it says test balance prins2 _5. So I can come down here and see that this is the test case that is actually failing. And now to parse what this means, whenever you see the assert in Python, If you have assert by itself, so I'm going to type Python 3, go into the interpreter. If you have assert like this and true, then this does not raise an error. Anytime you have assert and the thing to the right of it evaluates to true, then no error happens. But if you have assert and false, the thing to the right of it is false, then you get this assertion error thrown. And in this case, that's how PyTest knows that the test failed, is because we had assert, and then the thing over here to the right evaluated as false when it's supposed to evaluate as true. So this whole expression should evaluate to true, which means that this function right here should return false, but it is returning true. And because this is returning true, when you say not true, you get false. Assert false throws this error, the test case fails. So I need to make this function actually return false. And if we look at the example itself, we can see why it should return false. It's because these parentheses are not in the correct order. That this curly brace right here, this first one, should be to the right of this square bracket right here. And if it was to the right, then the parentheses would be balanced and it should return true. But instead, it is incorrectly returning true on this test case. So here, where it says where true equals balanced parens 2, this whole thing right here is giving this balanced parens 2 corresponds to this right here. And it's saying that this was returning true. This thing right here, returning true. That's what this true equals that indicates. And because this was true, we got not true evaluates to false, assert false, giving us this assertion error. Are there any questions about how to read just like what's in this error message? Okay, then the next thing that I'm going to do, the next thing that I always do when I have a test case that's failing, I always want to examine my code to figure out why exactly is it failing? What is it doing incorrectly that it, what is it doing? And the way to do that is to add print statements and add print statements everywhere. And so I'm going to go ahead and type symbol right here, and then I'm going to use that that Vim macro that we created earlier at P to go ahead and print the symbol that's getting printed every time. And let's go ahead and rerun the test cases and see what that looks like, that output looks like. And you can see that there's a lot of output now because so there were 4 failing test cases, and for each of these failing test cases, it's going to print a whole bunch of stuff. In order to make this output a little bit more manageable so that I only have to focus on one test case at a time, I'm going to modify exactly how I'm using this PyTest command. And in particular, I'm going to pass this -x command line argument to PyTest. Anything that you put in the bash terminal after the program that you're running is a command line argument. So in this case, the -m and PyTest are command line arguments to Python 3. And this -x is a command line argument to the PyTest module that is being run by Python 3. And what this -x does is it says, instead of printing all of the test cases that fail, only print the first failing test case. And so this makes running all the test cases faster, so you get faster development time that way. But it also makes it so you don't have to see all that extra output, and we can sort of just narrow our focus down into one test case at a time, get that one fixed, and then move on to the next ones. Okay, so yeah, we're printing out, when it says captured stdout call, this stdout is pronounced standard out. Standard out is anything that gets printed to the screen during normal execution of the program. So this print statement right here is actually printing to standard out, and normally standard out goes directly to the screen, but PyTest captures that and puts all of the output right here. So this is the output from this print statement right here. And this is, let's see, a little bit hard just by itself to figure out what's going on. So I'm going to want to print out more information than just the symbol. And in particular, I'm going to print out all of the information that we were looking at when we were doing this table before. So I want to print out the symbol, my current iteration number, and the values of the stack at every iteration. And printing out all of this was essentially printing out every variable that exists in the program, and that will help me walk through step by step to identify exactly what is the situation that the code is failing with. So in order to do that, I'm going to first modify my code with that enumerate like I had before, like this. So again, the I is the iteration number, the symbol is the actual piece of information from the text string. And then I'm going to delete that line right here. I'll actually just comment it out for now so we can compare and contrast. Normally I would delete it though. And I'm going to put all of the variables that I want to print out and inspect on a single line. So I, comma, symbol, comma, stack, like this. And now I'll press @p like that so that I print out all three of those values. So I'm going to undo that again so you can see the mechanics of what I did. Typed in I, comma, symbol, comma, stack, all the variables that I wanted to print. And I like to do it all in a single line. I think that makes it easiest to read. And then using that same macro that we had before, @p will print out all of those variables. And now coming back over to the right-hand side, rerun this, and here's the output. Oh, it's potentially a little bit confusing, so we'll go into the details of how to read this in a second, but just notice that there is one line per iteration of the for loop, and here we have I, comma, symbol, comma, stack. Here's the I, here's the symbol, here's the value of the stack.
Hey, Mike.
Yeah, go ahead, Jonathan.
On your Python 3-m pytest-x command, how did it know which file to run the pytest on?
Great question. So whenever you use the PyTest testing framework, it always looks in this tests folder, always finds Python files that start with test underscore and looks for test cases inside of those functions. And then inside of the that file, any function that begins with the name test underscore is going to be one of the test cases. So I could have other functions in here, say like not a test and return false or whatever it's going to do. And because this does not begin with test underscore, it's not going to get registered as a test case. For your homework assignment, let's say there are two different files, the test underscore main and test underscore extra credit. At the beginning, you probably don't want to be worried about the extra credit. You may not even look at it. It's totally up to you. If you want to look at only a single file at a time, you just specify the name of that file right over here, test/test underscore main, and it will do the run for that file. You notice that this is taking quite a long time to run right now, and that's because these print commands are actually fairly expensive from a runtime procedure. So they're not something that you want in your code generally, but they're good for debugging. In order to get back to the same sort of output that I had before, you can still just put that -x right there at the end, and it still just stops after the very first test case. So this command right here, including the name of the file or not including the name of the file, ends up being totally equivalent. There's this question in the chat about what exactly does the -x do, and the -x says that, so notice that it says there's only one failed test case and 4 passed test cases. So it ran exactly 5 test cases total. But in my file over here, I actually have 9 different test cases, 1 up to 9. As soon as it hit this test case 5, this right here, it realized this is a failing test case, and so it stopped and never even looked at all of these test cases down here. That's what the -x does. It says as soon as you hit one test case that fails, stop there and don't keep going. And when I'm sort of debugging, working on a homework problem, I will use this flag just so that I can focus in on one test case at a time and really quickly figure out what's going on with that one, fix that one, and then move on to the next test case.
Hey, Mike, is it possible to specify, so is it possible to single out a test case that failed after the first one? So say, for instance, you're having trouble debugging the first one. You want to
Great
move
question.
on?
Yes, so this PyTest has so literally hundreds of different command line arguments that you can pass into it. The two, though, that I think are the most useful are this -x, and I'm going to jump back over to our GitHub README here for a second, and let's just search for -x down here. The next one is this --max fail command. So -x stops after the very first test case that fails. Max fail stops after you reach whatever this number is right here. So if you can't work on the first one, or whatever reason the first one's difficult and you want to move on to a different one, then do the max fail 2. And then if you were to do that down here, --max fail 2, hit enter, it'll still run this first test case, but the very last one will be the next number 2 test case, and you can just focus on this one, ignoring this one here. And then, yeah, it's still a little bit easier to work with than the entire output by itself. And notice here that this running all these test cases with these print statements inside is taking a really long time. So it's much more practical just to use that max fail and stop after 2. Great questions so far. Any other questions? Okay, so yeah, let's rerun this with the -x, come over here and check out what's going on specifically. So here, what I'm printing out is actually all of the information from this table that we were looking at before, that there's this symbol variable, this I, and the stack. Since I was writing it out by hand before, I could give it a little bit more organization potentially, but each of these columns right here corresponded to a single iteration of the loop. And in my terminal over here, it's each row that corresponds to a single iteration of the loop. Some people like to, instead of putting all 3 of these things on the same line, putting them on different lines. But I think that ends up making it hard to read. I personally like to just know that one line is one iteration. And now what I need to do is I need to figure out why this is why this test case is failing. And we said before that this test case is failing because this is returning true when it should be returning false. This is being evaluated to true, and we know that because of this line right here. It's telling us that that function is equal to true, but this is not balanced parentheses in quotations, so it should be false. So somewhere it's getting to this return true statement when it should be returning false. And so now let's just kind of look at all of these examples line by line to see exactly which one of these lines the error is happening on. So here, when my symbol is the opening parentheses, then I want to push that onto the stack, and I can see that that's correctly happening, that on the next iteration, here's my stack, that opening parenthesis got pushed onto the stack. Then there's a square parenthesis right here, should get pushed onto the stack because it's an opening parenthesis, and here it is being pushed onto the stack. That all looks great. Here's another opening parenthesis, this time the curly brace, and it should get pushed on the stack, and it does. That looks great. Here, though, we have a closing parenthesis, in particular the closing square bracket. And at this point, when the closing square bracket, in order for, if the code was working properly, what it would do is it would see that this closing square bracket does not match this curly brace right here. And because this square bracket does not match this curly brace, it means that the input text cannot be balanced, or the input parentheses cannot be balanced, because we have a curly brace, and so if we have something that's closing, it must be a closing curly brace in order to be correct. So why would that, or how do we fix that? We need to add a check to see if this symbol right here does not match the corresponding symbol here. That's when we need to sort of panic, return false. We have found a situation that is not balanced. Right now, we already have a checking to see if the parentheses match like this. And if they do match, then we're doing the pop, and that's correct. But what we're missing is that, that part where if they're not matching, then they're not balanced. So at this point, it should be, whoops, else return false, like that. And that will check to make sure that now on this line right here, it sees that this and this do not match, and so go ahead and return false. Save that, :W, come back onto the right-hand side, rerun this test case, and now we can see that I've moved on to test case 7. So test case 5 passed, we passed that one, moved on to the next one. You can also see that the number of passing test cases before was 4 before it stopped, and now it's at 7 passing test cases. So we've made some progress, so that looks good. Before we look at this test case in detail, are there any questions about how I used this print statement right here and the output over here to figure out that what I needed was this else statement right here?
Yeah, just a quick one. I don't want to stray too far away from what we're talking about, but with that if statement where we're looking at the last index of our list, can you briefly explain why we use pop at the end?
Why we use what? Oh, why this right here?
Yeah.
Sure. So what this is doing is, let's go ahead and I'm going to open up an interactive Python. So this is another sort of useful debugging procedure when you're working with things, is you don't always have to just run the test cases. Sometimes you can just open up Python directly and run your code directly. In order to get access to the code that you're working with in Python, you have to invoke Python this way. Say python3-i standing for interactive, and then the name of the Python file that you're working with. And I hit enter, and now I go into interactive Python, and I know I'm in interactive Python again because I have these 3 arrows right here that whenever you have the $sign, that means you're in the bash, you're in the terminal, you type bash commands. Whenever you have the 3 arrows, you're in Python, you can type Python commands. And because I had parens3 right here, I have access to this function right here. And so I can call this function balance parens2, and let's just do a simple balance parentheses thing like this and hit enter. And here, this is going to illustrate the question about why exactly did we need this stack.pop? What exactly is it doing? So now I'm looking at a successful run through balance parentheses. We had balance parentheses inside of our string right here, and our function is correctly telling us that it's true, it is balanced. And how it's doing that is the key step is right here on I equals 2. And again, I know that I equals 2 because the order of my columns on the right-hand side is I, comma, symbol, comma, stack. So I is the very first one, symbol is the second one, and stack is the third one. Here, the, so I equals 2, so it's the third iteration through. And the symbol that I'm looking at is the first closing parenthesis. So it's this closing parenthesis right here. And in order to match this closing parenthesis, it must be another closing parenthesis to the left. And so what we do in this if statement right here, checking to see if this closing parenthesis type matches the opening parenthesis type. And in fact, it does. And so in order to get rid of this opening parenthesis type, we've already matched this one. We don't need to look at it anymore. That's why we do the stack.pop. It gets rid of the very last thing on the right. If we were to modify this program so that we had, say, square brackets and the innermost one, then on this line right here, we're pushing on the square bracket on iteration 2. In iteration 3, we get that square bracket. We know we're good because the thing on the right over here is the corresponding square bracket. But in order for subsequent iterations to know that we're done looking at that square bracket, we can go back to looking at this opening parenthesis. That's why we pop off this very lastmost thing. So after we look at it, after we acknowledge that we have found the match, we pop it off and can keep going.
Got it. Thank you.
Great question. Any other questions so far about anything?
So when you run the tests, is it only displaying the output of the tests you want it to run?
So is your question about in this section right here?
Yeah, yeah.
This is only the output for exactly this test case. Exactly, yeah. So you don't have to, and the key reason for that is because we're adding, when we do the PyTest, we're doing this -x flag. If we did not have this -x flag, then it would show us multiple test cases, and you'd have to sort of scroll through, look for exactly which one you're caring about. But because we've added this -x flag, it makes it very easy to just find, look up here at this red line, then look down for the dash line, and everything right here is just the test case, just the output of just this one test case and nothing else. Good question. Any other questions so far? Okay. So yeah, we're at this situation now where we still have a failing test case, but it's a new failing test case. So we've made progress, and but we still have more work to do. And now we can look at this test case right here and see that the situation is a little bit different than the situation we had before. So this fix right here didn't actually work for this example test case. The problem that we have here is that we have more opening parentheses than we have closing parentheses, that there's no matching situation for this opening parenthesis. Just to recall real quick, when we were looking at test 5, the problem was that we had a matching closing for each opening. They were just in the wrong order. So, so it makes sense that because the test cases are a little bit different, the solution is going to be a little bit different for them. And now looking at this output code down here, it's still, let's see, there's a lot of good information in there, and based on just this information, I could figure out what's going on. But I want to add a little bit more information now just to help illustrate some more debugging techniques. And that's that you don't need to put print statements just in one location, just in your for loop. Another great spot to put print statements is right before any time you hit a return value. In this case, our function here is returning true. Again, we know it's returning true because the output right here is telling us that. And so I want to know what are the values of all my variables right before the program exits. And so at this point right here, there's really only one variable that, that matters, and that's the stack variable. And so I'm going to go ahead and print out the stack variable right here. And again, I just type stack and hit the @p command in Vim to give me that nice print statement. And we'll save that and come over here and rerun that. And we'll see that we get this new output right here that happens just before the return statement. And the fact that I have these print statements that are explicitly telling me what all the contents of the variables are makes it really easy for me to just glance at this and say that, oh yes, this is the one that corresponded to the return statement right here. Since this is the very last thing that happens in my code, I could have figured that out without having these labels, but the labels are still make things much easier for me. And what I'm noticing is that I still have this parenthesis right here. And this parenthesis corresponds to the very first parenthesis that was on the stack that we pushed on in the first iteration right here. You can see that here we pushed on a second parenthesis, getting this. Here we popped off the parenthesis, going back to this. Pushed on a second parenthesis, getting this. Popped off that second parenthesis, and now at the very end we're left with just one parenthesis again. And so this one parenthesis corresponds to this one parenthesis right here that doesn't have any closing parenthesis associated with it. And the fact that there's anything at all in this stack means that there is something that we just didn't find a closing parenthesis for. So the first thing that I'm going to do is just think about, okay, maybe instead of, rather than trying to like think about how do I actually solve this problem, it's totally okay just to try random things and see if like random things can fix this for us. Because we have this really robust testing framework for us, I can just change this true to a false and see if maybe, okay, I know that we're returning true when we should have returned false. Let's just return false and see if that works and rerun this. And now I can see, oh, that was a really bad idea because now no test case is passed. I'm failing instantly. And so that's not going to be what my fix should be. Let's go back, change that to true. I never have to worry about accidentally breaking my previous test cases because it's really, really easy just to check to see that I haven't actually broken anything. And when I do break something, I know right away that I've broken it and can undo whatever it is that I did. So instead, we need to have something a little bit more complicated down here, actually checking to see whether the stack is empty or not empty and returning accordingly. So let's see, last time we did it in just a single line. This time I'll do I'll maybe a little bit more explicitly and say if the length of the stack is equal to 0, then return true, else return false. And let's retry that. And okay, that looks good. I passed those, or I didn't fail on this test case right here. But you can see that my code is still kind of like hung up right here. It's taken a long time to run. And so in order to explain why it's taking a long time to run, I'm going to go back over to our test cases and look at this very last test case. This test case is the more complicated one. All these other ones are just have a single thing inside of it. This one has a lot of code inside of it. And here, what it's doing is it's generating these very complicated tests. So in Python, when you take a string and you multiply it by a number, it sort of appends that many versions of the string onto itself that many times. So this is 10,000 of these parentheses, opening and closing. And then I'm just making a whole bunch of checks saying that, okay, if you have the open and the close, that's good. But then any other combinations of things is bad. And because this number is so big, it's taking a long time to run right now. So I'm going to press Control-C over here to stop that. And we'll come back over to here. And the key thing that's taking a long time is these print statements. We don't think of print as being something that's expensive to do, but it actually is relatively expensive to do. And so I'm going to comment out all of the print statements like this, and come back over here and rerun those tests, and now they pass instantaneously. Yeah, so when you're going through your own homework assignment, it'll probably take you a little bit longer to come up with like what is the right fix for whatever the particular problem is. But these are the same sort of steps that you should be going through of focus in on one test case at a time, figure out what you have to do just to get that one test case to pass. Once you get it to pass, rerun the tests, make sure that it didn't break anything previously, and use these print statements to sort of zoom in and inspect your code. There's a good question in the chat about what to do when your code is sort of running, taking a long time. And the answer is if you press Control-C on any Python program, it sends what's called the kill signal to the Python program and stops the program. So I'll write that out down here. Control-C sends the kill signal to end the Python program. I'm not sure if this has come up before, but this is a comment right here because it starts with a hashtag, and in both Bash and Python, comments are the same. They start with hashtags. Any questions about any of that debugging procedure? Okay. So the last thing I'll say about this is that at this point is when I would, this would be the first time that I would actually commit my code into Git and push it up to GitHub, and actually have the test cases run on GitHub. Notice that when I was doing all of these test cases here, I was doing them all locally on the Lambda server. That way you get this really fast instant feedback about whether the test cases pass or fail. And then it's only at the end, once you're pretty confident, like, okay, I know that the code works on the Lambda server, let's push it up to GitHub and it'll run its test cases on that big, using different versions of Python and different operating systems and making sure it runs on every sort of conceivable possible situation. If it runs on the Lambda server, unless you're doing something really, really weird, it should run on the on GitHub as well and pass the test cases. But you also don't forget that to do the flake8 command. So flake8 space and then the name of the file, parens.py. And so here I can see that there's a handful of things that it wants me to fix. And in particular, all of these comments that I have like this, those are things that they're great for debugging, but not things that you want in your production code. So you'll want to delete those before submitting your assignment. Any questions about debugging or the assignment or anything like that?
Yeah, I have a question. We talked about this last class a little bit, but can you review again, like if we're really having trouble debugging and we wanted to like copy our code into Python tutor, like how we copy and paste again? Because I think like you were trying one way, but it wasn't like the same if you weren't on a Linux computer.
Sure. So the key thing here is, like I said, there's maybe sort of two steps. There's a question about like, how do you actually copy something from your terminal into Python tutor? And that's something that's going to be different from operating system to operating system. But essentially on PuTTY, if you just select something, it automatically goes to your clipboard. So that's for people on Windows using PuTTY. If you just select text, it automatically goes to your clipboard. If you're on a Mac, then just selecting and right-click copy should be what you need to do. The downside of that, though, is that if you're using my Vim configuration settings, you have this problem of there's these numbers all the way, the line numbers on the left over here, and those will get copied as well. And you don't want those copied when you're pasting into Python tutor. So the way to get rid of these line numbers is the vim command. It's a colon command, so you type colon, and then no number, number. Let's see.
I think it was set no number.
Oh, thank you. Yes, set no number. No number is the name of the setting, and you actually have to do set in order to specify the setting. That you can see turned off the line numbers over here. To turn them back on, it is set number like that. And so this line right here, set number, that's in the Vim RC file that I have that I recommended you all download and install. Good question. Any other questions? Okay, then we're going to shift gears here and we'll start talking about this, this big O notation thing. And this is something that, so at this point, if you have the PDF file handy, that's what we're going to be looking at. And this big O concept is, well, I have a number of things to say about it. The first is that essentially, so for most Python and most programming contexts, concepts, the internet is great. For big O notation, I have not seen a website anywhere on the internet except Wikipedia that has a correct information about big O notation on it. So if you're just looking for Python concepts or help about Python concepts or programming in general, internet is great. If you're looking about big O notation, do not trust any blog source. References that you can use are, so these notes right here, Wikipedia is great, but it's a little bit over technical, very much approaching from the math perspective. And the book would be the sort of the real best intro level explanation that's not based on these notes right here. I'll try to point out some of the major misconceptions that the internet has about big O notation as we get to those concepts. But those are also the sort of concepts that, or those misconceptions are the things that when you're at, say, an interview, trying to get hired at Google or Microsoft or Facebook, if they come up and the interviewer notices that you have one of those misconceptions, it's like an instant red flag of this person probably doesn't have very much academic technical knowledge of computer science. Okay, so yeah, that said, we're gonna dive into the notes at this point. So what we're gonna do is we're gonna start by just doing some basic counting. And the idea of this is that counting will serve as a proxy for interesting properties of our program. And there are many different interesting properties that we can use big O notation for. The most common is like the runtime of a program. And so in order to measure as a proxy what our runtime is, we'll just count how many lines are going to get executed. So if we look at these first 3 lines here and just count how many times the X's are going to get printed, well, that's really easy. Just you print 1 X per line. So 1 plus 1 plus 1 is just 3. That's about the easiest possible situation. For loops are also relatively easy to count. We know that this range right here goes from 0 up to 9. So there are 10 total items inside of it. And that's really easy to get confused right here because even though we end at 9, it's still 10 items because we are including the 0 right here. So when we count how many Ys get printed, there's just 10 Ys being printed. The first somewhat interesting example we have is this one right here. And here it's sort of like a combination of the previous ones where you look inside of the for loop. So here's the body of the for loop. And for the body, there are 3 Z's. And then up here in our range, well, this range goes from 10 up to 19. So it's still got 10 elements in it. So range 10 to 20, same as range 10. So it happens 10 times. So we multiply the number inside the body times the number of times the body executes, in this case 10. So 10 times 3 is 30, 30 of these Z's. The sort of the takeaway rule from this is that if things are happening one after the other, add it together. And if things are happening inside of a for loop, you multiply by the number of times the for loop goes through. This next set of examples will build on that to be a little bit more complicated, a little bit more interesting. So here, there's 1 X inside this for loop here. There's a 1. So this for loop happens 10 times. Multiply 10 times 1, and we get this, whoops, that this whole first for loop happens for a total of, or print X a total of 10 times for these first 2 lines right here. Then for these second 2 lines right here, well, now this for loop happens for 20 times, still only 1 X, multiply those together, we get that it happens a total of 20 times. And then to get the total number of times that the X's are printed on all of them, you add that 10 and that 20 to get 30. So 30 X's get printed. Are there any questions so far? What I find often happens for students is that the very beginning of this discussion seems like almost trivial sometimes in what we're talking about. And then at some point, things, it's just like going off a cliff. Like, I'm totally lost and I didn't think I was lost a second ago, but now I don't even realize what was going on a second ago. So try to, even though this might seem a little bit trivial, try to keep engaged and pay attention, because it'll kind of set the foundation for the really hard parts coming up. Okay, so here we had for loops that happened one after the other, and the key idea was that if things happen one after the other, we sum them up. Here we have things happening inside of each other, and so with something's inside of something else, we multiply. So this for loop 10 times, 20 times, 30 times, and so the total number of times this y will be printed will be 10 times 20 times 30, multiplying all of these numbers together because the for loops happen inside of each other instead of one after each other. So we do that multiplication, and let's see, I think that's 600. And now this, yeah, here we go. Our last one right here with these z's. This one's getting starting to get more complicated, so we'll try to be really careful step by step. I'll write to the right-hand side of each line how many times just that line by itself is getting executed. So here, this print statement gets executed once. This for loop will happen 10 times. This print statement here once. This for loop here 10 times. A 1, a 1, a 10, a 1, a 10, and a 1. And now I'll go through and group all of these things together using the rules of the addition and multiplication. So here, this print z right after this print z, so add those together. Both of those together is a 2. These print z's happen inside of this for loop, so it's inside, so it's multiplication. So these 3 lines together get grouped into a 20. Come down here, this one is inside of this. Those get grouped into a 10. Multiply 1 times 10, you get 10. Now these, I'll do all 3 of these lines, and it'll be a little bit hard to see exactly what I'm grouping together, so I'll draw an explicit box around it like that. It's the entire body of this for loop right here, including this print statement. They're all happening one after the other. First this, then this, then this. So we add it together. So 1 plus 20 plus 10 equals 31. And then down here, this one, 10 times 1 is 10. Up here, we still have that 1. And oops, I'm skipping just a little bit of a step. I forgot that this 31 right here is only the inside block. It's inside of a for loop, so we have to multiply it together with that for loop. Again, I'll draw this little box right here to remind me what's getting multiplied together. So 10 times 31 equals 310. And now this 310, this whole big for loop block, is happening sort of sequentially. First this line, then this block right here. So we add it all together, and the whole thing overall is 1 plus 310, 311 plus 10, 321.
Professor, isn't 2 6,000, not 6,000?
Yes, great correction for me that there are 3 zeros over here, so there needs to be a third 0 right here for 6,000. Any other questions about these sort of counting problems right here? Okay. The next way that these sort of problems become more interesting is that rather than just having numbers inside of these range functions right here, we have variables. And so that's what the next page is going to do. So here, it's the same exact functions that we had above, but now all the 10s have been replaced by this variable in, which is sort of a number that controls how long our code is going to run, how many print statements we're going to have. So here now, going through that same procedure, write down the number of times that this is going to execute this for loop right here. Now it's a variable expression instead of just a number. So it's in right here, 1 right here, multiply those together, we get, that's just equal to in. Here we get 2 in right here times 1. So that whole thing's equal to 2 in. Add those together, we get 3 in as the number of times x will be printed up here. Yeah, I do the same sort of calculation right here, and you'll get, so in, again, we're multiplying all of these things together. So you multiply them together and you get 6 in cubed. And then this last one down here, there's the complicated one. So there's a 2 and an in, multiply those together, you get 2 in. Then we'll do this for loop, just a single in times a 1, so that's equal to in, and then just a 1 right here. So box all of that out again, and that's added all together, 3 in plus 1. That's all inside of this for loop right here, which takes in, or runs for in iterations. Because this is inside of this, we'll multiply them together, so that's equal to 3 in squared plus in. And then we have a 1 up here, and this whole thing is an in. So add all that together, and you get 3 in squared plus here in, 2 in, 2 in plus 1. And hopefully, if I did all the math correctly, if you substituted 10 for in all of these equations, you would get back the same numbers that we got in the first page above. Any questions about this so far? Okay. This next page, things are getting even more complicated now, because if you look at these ranges over here, you notice that the amount of time this inner loop, this J loop right here, how many times it's going to run, is going to be different every iteration through of the loop. Before, our range was up above, the range looked like this, range of in. So it did not depend on I, did not depend on which iteration we were doing. It was always going to be the same number. Now it's a different number. And these are down here, sort of 3 different ways that these different numbers can happen. If you have your i's and your j's as the ending spot of the range, so range from 0 to I, remember that's going to be 0, ... up to I. But down here, this is an even more complicated one because it's going to start at I, then I plus 1, and so on until you get to in. And then down here, you get like the really, really nasty of I plus 1 up to j. So here it's just the ending that's changing. Here it's just the beginning that's changing. And here it's both the ending and the beginning that's changing.
Hey, Mike.
Yeah.
Isn't the range function in Python exclusive of the end?
Yes, great point. So here I wrote 0 to I. All of these end values that I have out here should be -1, like this, because the range does not actually return the whatever number is on the rightmost side. That's a great correction. Thank you. Any other questions or comments at this point? Okay, so the takeaway, or what, let's see, we could count these values directly. There are formulas that we could use to do this. And when you take the discrete structures course or discrete math course, this is a required course for data science majors, optional for people who are doing the sequence though. If you were to take this discrete math course, you would come up with different ways to actually count these numbers exactly. But for our purposes though, we're just gonna say it's too hard. We're not gonna count these numbers exactly. And that's where the big O notation is going to come in. It'll help us in these situations, counting how many times something is going to happen. So not going to do it, too hard. And we'll see that not only is it too hard, it's actually not useful to count it exactly. That the big O notation will give us good approximations for all of these numbers, and those approximations are actually more useful than the exact numbers themselves. Okay, so that's sort of like the main motivation for starting to talk about this big O notation stuff. And yeah, what we did a second ago involved code, and so it was maybe obvious how it would translate into Python programming. We're going to switch away from talking about code to talking about kind of a pure math concept here for a couple of minutes. And so it's not going to be obvious at first how this ties into what we were just doing, but on next week on Monday, we'll make that connection together. And this is one of the key things, this sort of like math idea, what do these notations mean from a math perspective? This is one of the key mistakes that everything on the internet, except the sources I mentioned before, is wrong about. So really need to understand the fundamentals of the math here. Understand the math and not just the applications. And then so that's sort of like the key thing that you should be focusing on, like personally, as we're going through this. The key idea of why we want this big notation, what is it going to do for us, is it's going to give us an approximation for those complicated formulas that we saw above. I guess we didn't see the formulas, but the situations that we saw above. And these notations, they are general like math concepts. They are not exclusive to computer science. Statisticians use them all the time. If you go on to take the data mining course, we will be applying these to statistical problems combined with programming problems. And so, yeah, it really is important to understand this sort of like where it comes from a math perspective. And right down here, I'm going to draw sort of like the key plot about the intuition of what these functions are going to do for us. And in green, I'm going to draw a relatively complicated function. So it's got a whole bunch of squiggles like this. And this is a really nasty function, one that we would not want to explicitly, if we call this function f, we would not want to actually try to figure out what is the formula for this f function. It's just too nasty to try to figure that out. So instead, what we want to do is come up with another function that it's like basically behaves kind of like how f does. So in this case, f is basically like a straight line with some wiggles in it. And so this red function here, g, called g, is a great approximation for f. At any given point on the x-axis, it's really close to f. And so if we just worked with g instead of working with f, then we can have a nice clean formula. Looks like I did something like g of x is, well, it's not exactly equal to x, but we'll call it something like that, g of x equals x. And that's much simpler than this, whatever this green formula is, but still gives us a good idea of what's going on. And so our motivation with this whole notation is to work with these simple functions instead of these complex functions. We'll see a lot more plots like this throughout these notes in order to give us more concrete examples of where that's happening. Here, we'll start with the actual formal definitions now. So we have two functions, f and g. They're both functions on the positive real number line, so r plus to r plus. So they're not taking negative values and not returning negative values. And if you take the limit as x goes to infinity of the ratio of these two functions, if it's less than infinity, we say f equals O of g. If it's greater than, f equals omega g. And if it's possible to be both less than infinity and greater than 0. And in that case, we say f equals theta g, because f equals both O of g and f equals omega of g. So this is the formal definition that we'll need to turn to quite a lot when we're actually talking about how to compare two functions to each other. But we'll see some intuition here in a second about what these definitions actually mean. Before seeing the definitions though, let's just work through some examples with these actual these definitions here. So here, if we have f of x equals x, g of x equals x squared, so x divided by x squared, we simplify that, we get 1 over x, and in the limit, as x goes to infinity, 1 over x equals 0. So here we have that 0 is less than infinity, but it is not greater than 0. So we are in case number 1 up here and not case number 2 or case number 3. And we would say that f equals O of g, or x equals O of x squared. Yeah, so again, the intuition for this takes a little bit while to build up, but are there any questions about just the mechanics of what we did here, how we plugged things into the definition right here to say that how these two things are related? Okay, so doing the same with example 2 here, we have x squared and x. So x squared over x equals x, and the limit, again, as x goes to infinity, 1 over x, whoops, sorry, that should not be 1 over x, that should just be x. It's only x by itself because that's what our simplified f over g evaluates to. That limit is equal to infinity. So here, infinity, not in the first case, infinity is greater than 0, so we are in the second case, and not in the third case. And now we say that f equals omega of g, or x squared equals omega of x, like that. One of the sort of principles that it's sort of really easy to prove, and we just kind of illustrated, is that if f equals O of g, then it's guaranteed that's entirely equivalent to saying g equals omega of f. just because if you have something that is less than infinity, you take, instead of f over g, you do g over f, you're guaranteed to get something greater than 0. Any questions so far?
Could you repeat that last proof? I didn't, not the proof, the like what you wrote in red.
Sure. So the one of the sort of principles, one of the kind of rules of thumb that is good to just have in your back pocket is that anytime f equals O of g, it guarantees that g equals omega of f. That O and omega you can think of as, in some sense, like backwards things of each other. And the way that when we start talking about the intuition that you'll want to be developing is that O is like less than or equal to, and omega is like greater than or equal to. So this is like saying f is less than or equal to g, and this is like saying g is greater than or equal to f. So just like you can swap the direction for inequalities, you can swap the direction for O and omega, like this. I think this is probably a good, we're pretty much out of time for today. So rather than trying to squeeze in a couple more examples, I think this is a good spot to stop, and we'll pick up here on Monday. If anybody does have questions about this, happy to stick around and answer them. Office hours is right now, but otherwise that'll be the end of our course for today.
Thank you, Mike.
Thanks, Mike.
You're welcome.
Bye, Mike.